Hey everyone, I am really excited about the unit we are starting today. In chemistry, we learn how to calculate a lot of things as far as maybe acids or reactions or equilibrium or all sorts of changes. But this unit talks about why these changes happen, like what's the driving force behind them. And it's all about flow of energy. Maybe you've heard of the term entropy before. Well, this unit is going to talk a lot about that and its role in driving processes that happen naturally. Now, I need to tell you right off the bat that this is not an easy unit. Many teachers avoid teaching this unit to any depth at all. I remember when I had it, it really just involved a few formulas and I didn't really understand what was going on, and it really was kind of a waste of time to even cover it at all. But I think it's pretty valuable to understand when you're studying chemistry why reactions happen and why chemical changes happen. And if you can stick with me, this unit's going to reward you a lot at the end once you finally understand what entropy is and why it matters. So some can-do statements, things I hope that you will be able to do by the end of this lecture. I can explain what a spontaneous thermodynamically favored process is and give some examples. I can describe what a microstate is and relate it to Boltzmann's principle, the second law of thermodynamics, and entropy. I can use statistics to explain why during spontaneous processes, energy flows from areas of higher concentration to lower concentration. And I can provide at least 4 ways of increasing entropy from a microscopic perspective. Now, I know all of the things I just said probably make no sense at all, but I think by the end of this lecture they should. First, we're going to talk about what a spontaneous process is, and the other word for this is thermodynamically favored. One of the criteria is that it doesn't require any outside energy to keep it going. It might take energy to start it, but once it's going, it doesn't need any outside energy to keep going. And how quick it happens has nothing to do with it. It could take years or centuries and still be spontaneous. And like we said, it might require outside energy to start. Here's some examples of spontaneous processes that you're pretty familiar with, I think. One is a ball rolling downhill. This is kind of neglecting friction and rocks that might be in the road or those kinds of things. But in general, once a ball starts rolling downhill, it's not going to stop until the hill is not inclined anymore. We can say that the ball had potential energy when it was high up in the air, and it changes to kinetic energy, energy of motion, as the ball's rolling down the hill. There's some heat transfer from friction as well. The next example is hot chocolate poured into a coffee cup. The hot chocolate cools slightly and the cup heats up until they are the same temperature. Maybe you've never really thought about it, but your cup warms up just as much as the hot chocolate cools down. What's happening? The kinetic energy of the hot chocolate molecules, which we call the system, is transferred to the coffee cup molecules, which we call the surroundings, until the temperature is equal. Another example is ice melting at room temperature. Here we're also having heat transfer from kinetic energy of air molecules, which we call the surroundings, to kinetic energy of water molecules. Here the water molecules are the system. And potential energy changes of the water molecules as they get further apart in the liquid than in the solid. And we talked about that during phase changes when we saw that the molecules are much further apart in liquids than they are in solids, where they're all locked together very closely. Another example is air leaking out of a tire with a hole in it. Kinetic energy of air molecules. The air molecules are always moving around, and they get spread into a larger volume of the atmosphere. So they were contained in a small volume of the tire, and then they go to a larger volume in the atmosphere. Cream spreading out into coffee. So you put a little splash of cream in your coffee, and at first you see the little swirls, and then finally your coffee is all the same color. And what's happening is that the milk molecules, which here we could call the system, spread their energy into the larger volume of coffee. Finally, wood burning and oxygen. So a lot of things can burn. Burning is an incredibly complicated process, but basically here you have higher potential energy bonds in the wood and oxygen in the air, and they rearrange to form lower potential bonds of carbon dioxide and water. Also, heat energy is transferred from the reacting molecules to the air molecules, which here the air is the surroundings. The complex wood molecule is turning into many more smaller molecules. Here we can call them energy carriers if we want. And specifically, they're carbon dioxide and water vapor. Okay, so the wood solid is turning into carbon dioxide and water vapor gases that are much smaller than the wood, and they go all out into the atmosphere. And that's because the wood is confined to a small space, but it turns to carbon dioxide and water vapors that spread out into a much larger space. All of these spontaneous processes obey the first law of thermodynamics. Remember that said that energy can change into different forms or be transferred to or from the system and surroundings. We talked about the first law quite a bit previously. But the thing about spontaneous processes is that they never happen on their own in reverse. Like, some things can go in reverse, but extra energy must be added from the surroundings to make it happen. We talked about wood burning in air. During photosynthesis, trees can grow, making wood from carbon dioxide and oxygen. But that doesn't happen spontaneously. If there's no sunlight, then the trees aren't going to grow or even exist. And we talked about a tire deflating. You can reflate the tire, but it's going to take some energy from either an air pump or a human pump to pump the tire back up. The molecules wouldn't ever just go from the atmosphere back into the tire and create a whole bunch of pressure and pump your tire back up. The thing is, the first law wouldn't actually be broken if those things happen. Energy is just being transferred from one form to another. But we know that they don't happen on their own, so we need some sort of other law to describe what's going on. And that law is the second law of thermodynamics. Now, we're going to spend most of the rest of this unit talking about the second law, and there's a whole bunch of different ways that you can interpret the second law. But the first one today, we're going to talk about statistics and the atoms and molecules on a microscopic basis. And I know most of you probably don't like math. Here, the formulas aren't really so important as much as what's going on. And I'm going to show you with the examples and a bunch of pictures. Okay, so if you get lost, then pause and go back to the slide before and try to figure out what's going on with the pictures. We're going to use this analogy first. Imagine that you have this super smooth pool table, so there's no friction. And when you hit a ball, its momentum is going to keep it going in a straight line at a constant speed until it hits something. And on this pool table, we're going to say that there's no pockets for it to fall into. Now, say we're going to have a white cue ball on the table and hit it. And we're going to just snap a whole burst of pictures like on the iPhone. Frame by frame by frame, we're going to watch what happens. So say we have our white cue ball, and it's the only ball on the table. And it's just moving all around, hitting side, hitting side, hitting side. And between hitting the sides or the corners, between the hits, it only goes in a straight line at a constant speed. And if we just kept bursting pictures on the iPhone, about half of the pictures would show the ball on the left side of the table, and half of them would show the ball on the right side of the table. So we can say that the probability is half that it will be on the left and half that it will be on the right. Now let's consider that there's 4 balls on the table. So you hit one, and it knocked all the other balls, and all the other balls are moving. And you give them a while to kind of get into equilibrium and kind of do their thing, and then you start taking bursts of pictures. Then we're going to divide the table in half and ask what's the probability that they'll be on the left side of the table or the right side of the table, versus equally on both sides. If we follow the table here in the picture, I've labeled the balls different colors, each of the 4 balls different colors. And we can see on the top row that there's one way that all 4 balls will be on the left side. And on the bottom row, there's one way that they'll all be on the right side. And then on the second row down, we see that if we want to say that there's 3 balls on the left and 1 on the right, then one way, like one of the balls could be blue, yellow, and green on the left, and the red ball would be on the right. Another way, it would be a red, blue, and yellow ball on the left, and a green ball on the right, and so on. And there's 4 different ways that this could happen. 3 balls on the left and 1 on the right. And then in the middle row, we're saying it's spread out evenly. Because the balls are all different colors, there's different ways that this can happen. So one way would be a red ball and green ball on the left, and a blue ball and yellow ball on the right. And then another way might be a red ball and a blue ball on the left, and a green and yellow on the right, and so on and so on and so on. And so there's 6 ways that the balls could be appearing that they're spread evenly, 2 and 2 on each side. And then if we want to say that we want to evaluate how many ways it could be 3 balls on the right and 1 on the left, well, that would be just like the 3 on the left and 1 on the right, 4 ways. Now we have all of these ways. We had 1 way it was all on the left, 4 ways it was 3 on the left, 6 ways it's evenly, 4 ways on the 3 on the right, and 1 way all on the right. That's a total of 16 different ways. Well, if we look at the probability, 1 out of 16 ways, it's all on the left. That's 6%. 4 out of 16 ways, 3 are on the left and 1 on the right, and that's 25%. And 6 out of 16 ways, they're spread evenly, and so on and so on. So we can say that the highest probability, a 38% chance right here, is that they will be spread evenly. Now, is there a probability that they could be 3 on the left and 1 on the right? Well, yeah, 25% is not a low probability. It's not impossible, even that they could all be on the left, 6% and 6% on the right. And here, what are configurations, the middle column, is all on the left, 3 on the left, 1 on the right. Basically, we're not looking at colors with configurations. We're not saying that the balls are different. We're just looking at the numbers. Where we use this term called microstates here, and that is individually labeling the balls, okay? So different microstates can produce the same configuration, okay? So again, microstate versus configuration. Microstate would be red ball on the left, configuration 1 ball on the left. Or microstate could be yellow, green, blue on the right, and configuration 3 balls on the right. So that's why under configuration I have all the balls black, because we're not really saying which ball is which. All right, already a little bit complicated, I realize. Now we're going to put a bunch more balls on the table. We're going to put 10 balls on the table. Okay, remember, we're hitting them, letting them just keep moving, and then just taking bursts of pictures. Burst, 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 burst. Okay, and then we're just looking at all the pictures and dividing the pictures in half and seeing how many balls are on each side. Okay, now on this table, there's no possible way that I can color the balls because there's 1,024 different ways with just 10 balls that they could all be either on the left side or the right side. So I'm not going to go through every line on the table, but you can see that there's only one way that the balls could all be on the left. And we said that there's 1,024 different microstates, 1,024 ways that all these balls could be on the table. So that's only a 0.001% chance that they're all on the left. Will one of our pictures show them on the left? Maybe 2 pictures will show them on the left if we took enough pictures. But chances are only 1 out of 1,024 of the burst pictures would be showing them all on the left. And the same would be if they were all on the right. It's extremely unlikely, not impossible, but extremely unlikely. And so if we look at the middle row, them spread evenly, there's a 25% chance that they will be spread evenly, 5 and 5. Now, let's go to the second most likely. We have a 21% chance that maybe it'll be 6 and 4, or a 21% chance 4 and 6. Okay, so that's also probable, but the all on the left or all on the right, we're getting pretty improbable here. Okay, so these are just pool balls, and we're imagining that they were on the table, just moving nonstop because there was no friction, and we're just taking pictures. But now, let's think about gases and gas molecules. Think of a mole and how many molecules it actually is. There are so many to look at, okay? And let's say that we have molecules and they're ideal gas molecules. And remember when we studied gases, we just said ideal gases, one of the criteria was that they don't interact with each other as far as pulling each other together or having friction when they knock into each other. They're just little points, they knock into each other and keep it moving like pool balls. Okay, so here we have a little experiment. In the top, we're going to start with 1 mole of ideal gas molecules on the left side. And on the right side, there's no gas molecules. And actually, that's what we call a vacuum. That's what we call a vacuum. A vacuum isn't suction, it's the absence of anything in a space. Okay, it's no air molecules there. And of course, we know from the kinetic theory that the gas molecules are moving all different speeds, all different directions. Okay, and what we're going to do in the experiment is that we're going to open the stopcock, and that's just this thing in the middle, the little gate. We're going to open it so that the gases can go to and from both different sides. And because they're all moving, eventually they're going to spread out evenly. And once they've spread out, once we give them some time to get into equilibrium, then we're going to take some bursts of pictures. But the thing is, when we take our bursts of pictures, it's all pretty much going to look similar. It's probably going to be half and half. But why do we think that that is? Well, we need to think about it statistically, and we'll get a little bit further with that in a second. First, I want to ask, what's the probability that they're all going to move to the left on their own? Okay, so we had them down in the bottom, and then remember they're all moving, so is there a probability that spontaneously, randomly, they could all go back to the left side again? Okay, and then what's the probability that they will be distributed between the two bulbs? So actually, our friend that you might remember, I don't know, from middle school or from statistics class called Pascal's triangle can help us with this. And that's just because we're considering a left side and a right side. You can see that if there were 2 particles, them both being on the left would be 1, and them both being on the right is 1, and then them being spread out evenly, there's 2 microstates, 2 ways that could happen. Ball A on the left, ball A on the right. Ball B on the left, ball B on the right. Okay, and then once we start going, we can go to 4 particles, and we see the distribution we showed before. This was the pool table example with 4 balls where we had 1, 4, 6, 4, and 1. And then we also did our 10 particle example where we had like 0.01% and 0.01%. Now it goes up so fast. So 2 particles was 2 in the middle, 4 particles is 6 in the middle, 10 particles 252. Look, if we go to 50 particles, all of a sudden we're at ranges of 10 to the 14th. Okay? And if we go to 1 mole, we're not even at 6.02 times 10 to the 23rd. We're at 2 raised to the 10 to the 23rd, which is far more than a mole. Okay? 2 to the power of 10 to the 23rd. Okay, so that's how much for them evenly spread in the middle. That's 2 times 10 to the 23rd ways that they could be evenly spread. And then we have 1 way that they could all be on the left, and 1 way they could all be on the right. Is it absolutely impossible that they could go on the left? No, but common sense would tell you that's never going to happen. No human would ever live to see this happen, okay? We would never find them all on the left. We would also only find them with the dominant configuration in the middle because all the other ones are going to be so unlikely. Okay, actually we didn't calculate it here, but even the next most probable configuration, maybe 1 ball less and 1 ball more on the right, is actually so drastically less than 2 to 10 to the 23rd that it's actually statistically almost impossible as well. This scientist Boltzmann was an absolute genius. He actually was a mathematician, a statistician, more than even a scientist. And he founded his theory before we even knew for sure that atoms existed. So there was such a controversy at this time that he just called them points, and they were moving around, and he was not even concerned with their existence more than just talking about statistically. If they were there, what would happen? he coined that term microstates, okay, microstates, and he said that all of them are equally probable. Okay, so this would be like all of the gas molecules moving around, and you just start taking pictures, and whether molecule A is on the left or on the right, it's equally probable. Okay, but the difference is, remember we talked about configurations. Okay, so whether molecule A is on the left or A is on the right, that would be a microstate. Okay, but the configuration would be 4 on the left and 3 on the right, or 1 mole on the left and 1 mole on the right. And that's a configuration. And some microstates gave the same configuration. Also, some configurations are more likely because more microstates make them possible. So even when we had the 4 pool balls, it was more likely that they would be half and half, 2 on each side, than all on the left side or all on the right side. And because we're talking about moles of molecules, huge, huge numbers, the dominant configuration, the one in the middle, is the only one humans would ever observe. All the other ones are so statistically unlikely. We talked about macroscopic state variables in the past, and we'll talk a lot more about what state variables are a little bit later. But basically, volume, pressure, temperature, enthalpy, and what we're going to talk about in a minute, entropy, they all reflect the dominant configuration. Basically, if we're measuring the pressure of something, we're measuring the pressure assuming that the molecules are in the places that statistically they would be. The thing is, like pool balls, maybe the 2 balls are equal momentum and they hit each other, and one stops because of the angle that it's at and the other one goes twice as fast. They're constantly going to be changing energy levels every time they hit, and they're going to change their position as well. But as a whole group, they're going to maintain the dominant configuration, and that's what we call the equilibrium state. Okay, so equilibrium state doesn't mean the molecules themselves aren't changing, but as a group, they're not changing. Boltzmann described entropy. This is a new term. We're going to spend the rest of this unit talking about entropy in all the different ways that it can be defined and used. Boltzmann defined entropy as the number or amount of accessible microstates. Another word for accessible is available. Okay, the amount of available microstates. He called that entropy. And the equation he gave for entropy is that S, which is the variable we use for entropy, is equal to a constant. This was later named Boltzmann's constant in his honor. S equals a constant times the natural log of the ways the configuration can be made. And we'll say ways are microstates. Okay, so the natural log of the number of microstates that could make that configuration times a constant. And this constant was later defined to be R, the universal gas constant, divided by Avogadro's number. Now, I know that some of you have not probably gotten past studying natural logs or logarithms in general in Algebra 2 or college algebra. So for those of you who have not, this formula might look a little strange, and that's fine. But the rest of you who are in pre-calculus or calculus or into the second half of the year of Algebra 2, this might look familiar. And when we're talking about logs, the only reason we talk about logs is because numbers are so huge, we're just talking about the powers they're raised to, because the numbers themselves, the digits, have less impact than actually the power they are raised to. One property of logs is when you subtract them, you can combine them into a fraction. Okay, so here, if we're going to talk about the change in entropy, then we're going to talk about Kb times the natural log of the final number of ways minus the natural log of initial number of ways. Well, when you subtract logs, what's inside the log can just get divided rather than subtracting. Okay, so it's kind of just like combining things with algebra. So here's an example. Okay, so we're going to say that in the final system, there was twice as many microstates, twice as many possible available ways that the molecules could be. And this example that we had where the gas molecules went all from being in one cylinder to being in two different cylinders is a good example of that. The way that we would do that is that there's twice the number, so 2 would be in the numerator, so 1 would be in the denominator. And if you calculate that out, you get 0.69 times the Boltzmann's constant. And that is the change in entropy, how much more entropy there is. Conversely, if you halved the number of microstates, so maybe we took a 1 liter container and squished it down to a half a liter, then it would be minus 0.69 times Boltzmann's constant. All right, so I know that this is a lot already. So right now we've just talked about where they were. And the thing is, where the molecules are is only part of the story. We also have to talk about the fact that they're moving. When molecules collide, their position and their energy change. And energy and momentum are kind of two ways about talking about the same thing. Momentum here, the formula for that is mass times velocity. Remember, velocity had a direction. Okay, so imagine you had a 1 kilogram ball and it was going to the left at 2 meters per second, then its velocity would be minus 2 kilogram meters per second. And if you had the same 1 kilogram ball and it was going to the right, we could say it was going positive 2 meters per second. So the momentum would be positive 2 kilogram meters per second. Energy is kind of the same thing, but instead we're going to square the velocity. And anytime you square something, the sign falls off. Okay, so if you square minus 2, then it just becomes positive 4. If you square positive 2, it becomes positive 4. Okay, and so the formula for energy is half times the mass times the velocity squared. And what we end up getting is positive results for everything. And sometimes we want to know the direction and other times we don't, but all we're talking about here is that things are moving and their mass and their velocity, they all matter. When molecules collide, we said, their position and their energy changes. And we're still going to imagine pool balls on the table now. And we're still going to be taking bursts of pictures. But now we're going to imagine that we have a radar detector on the camera. Okay, like a policeman's radar detector or a laser detector. We're going to describe the balls by where they are and then how fast they're going and in which direction. Here we have a pool table, and on the top picture, we hit the cue ball. The cue ball is going 100, say, miles per hour to the right, okay? And all the other balls are just sitting there, and their speed is 0. And then you break, and all the balls are going all over the table, okay? And that's the middle picture. They're all going at different speeds, different directions, and they're at different locations. Okay, so this is a more complete picture of the microstate. The microstate before, we just said where they were. Now we're adding which direction and how fast. The single motionless triangle that we had at the top is now 10 separate balls moving all over the place, all with their own energy, their own direction. Havoc is happening. What would be the chance that all 10 balls would come back to a triangle, stop, and eject out the cue ball at 100 miles per hour the other way? Well, it's actually not impossible. It's not. But it's just so improbable that we would never see it happen. Common sense would tell you that won't happen, but it's not impossible. Now let's talk about entropy change. I know we talked about Boltzmann. You got some logarithmic formula about number of microstates and logarithms and some constant. I know that probably didn't make sense right then. Right now we're going to talk about entropy a little more practically. We can say entropy, this phenomenon, the number of ways that things can be arranged, that energy can be arranged and that the molecules can be arranged. Well, one way is when it spreads to more energy carriers. And I want you to really focus on this word for this chapter and think of molecules and atoms as energy carriers. That's one of the principal things. Please consider that in this unit. That molecules and atoms, because of the kinetic theory, are always moving and they're always carrying energy. If one thing splits into two things, okay, so say we have a bigger molecule of dinitrogen tetroxide, okay, N2O4, and it splits up into two NO2 molecules, well, now there's two things going all over the place. We say that there's higher entropy because there's more ways that two things can be going, more directions they can be going in, different amounts of speeds and different places they can be than just one. So when the number of energy carriers increases, then that entropy increases, the ways that they can be arranged. And then number two, we have the energy carriers spread out in physical space. So if there's a bigger place that they can be in, then there's more locations they can be in. One way is actually when things change phases. So we have 1 mole of liquid oxygen, and we add some heat, and then it becomes a gas. Well, remember, 1 mole of liquid oxygen is a relatively small volume, but when we change it into 1 mole of oxygen gas, that's 22.4 liters. Okay, so we're going on the range of like 1 or 2 liters to 22.4 liters. So there's way more places that the gas molecules can be. There's all sorts of different pictures that could be taken, and a whole bunch of ways. So if we say the ways that the oxygen molecules can be spread out in space are greater, then we can say that the entropy is greater. So again, when the energy carriers, the molecules or atoms, spread out in physical space, there's more ways that they can be arranged, so the entropy increases. Okay, so we're almost there. We just have a little bit more to talk about. We were talking about the entropy is getting more and more complicated. First, we talked about just taking pictures of the positions. Then we talked about the pictures being like a radar detector. And then we talked about the fact that there was all different velocities, all different numbers and directions. But now let's focus on the distribution, okay, how those velocities are arranged. So not just in space, the numbers themselves. So some people say that molecules have like a position entropy and then an energy entropy, as though they're different. It's not actually that they're different. It's just that the human brain has a hard time like examining multiple things at the same time. So sometimes it's easier just to analyze them one at a time. The strange thing about atoms and molecules is that they can't just go any speed like a cue ball or a car. Like in the car, you just push the gas to any amount and the car goes from 0 to 25 miles per hour. It could be 22.4 miles per hour or 21.3 miles per hour. It can really be any speed. It's a continuous spectrum. But really strangely, and this took scientists years and years to figure out, and it's one of the greatest accomplishments in the history of mankind, is finding that when energy is transferred to or from atoms or molecules, it's actually like turning the fan switch in the car. Okay, so you think about it. You can only turn the knob to a number. You can't just put it anywhere in between. Okay, and there's a word for this in science that we say that the energy levels are quantized. This means there's a certain amount of energy called a quantum that must be added to go to the next energy level. It's like you turning the fan from 1 to 2. You'd be like adding a quantum of fan energy. Okay, or like if you're walking up a ladder, like you go to the next step. You can't just hang out between steps. One thing, remember from kinetic theory, that the temperature is proportional to the average speed of the molecules. So some are going to be going faster, some are going to be slower, but there's an average somewhere. And these graphs talk about that distribution. Let's look at the graph on the left first. The left has 2 scenarios. One is a scenario of a whole bunch of gas molecules and they're at 300 Kelvin. Remember, some are going to be going faster, some are going to be going slower. And that's why if we look at the bottom, the speed, some are going to be going fast, maybe over here, some are slow. Okay, and then the y-axis here is the number of molecules. So there's going to be a lot that are going kind of in the middle. Okay, and a few that are going real fast and a few going real slow. Okay, but the next scenario is that we're going to increase the temperature to 1,000 Kelvin. When we do that, the range is way bigger. That's why the graph gets much, much wider. So there's still in the middle, we're going to have the highest number, but things start spreading out. And so there's more possibilities once you raise the temperature, more possibilities of speed. The next graph in the middle, all we're doing is just rotating this graph sideways. So we're flipping the y and the x-axis now. Okay, so speed is now on the y-axis. Now, the third picture just imagines if we put little tiny gas molecules into, instead of just drawing a line. So you still see the 300 curve here and you can still see the wider 1000 Kelvin curve there. So we can see that these are the energy rungs of the ladder here. So remember we said they can't just go any speed. So they can either be going speed 1 or higher up speed 2 or speed 3. Okay, but you can't just be in the middle. Okay, the atoms have to sit like stepping on the rungs of a ladder. Here's the key. Remember we talked about the atoms or molecules being energy carriers. At higher temperature, like 1000 K, the carriers are more spread out. Energy is spread out. If they are spread out, that is increased entropy. Okay, spread out. Almost there, almost there. I promise we're almost there. Okay, this next picture talks about the way that they can be spread out. The way that we had it on the previous graph was a nice bell curve. This way just shows, just like how they could be spread out on half and half of the pool table when we looked at their position. Well, each molecule could have a different speed, okay? And this looks at the way that they could be spread out. Okay, so here we're just going to have a total of 3 quanta of energy and 3 molecules total. On the top, one molecule has all the energy and the other 2 have 0. On the bottom, each one has 1. And then in the middle, the green one has 2, the black one has 1, the white one has 0, and then you keep going. Okay, so these, each individual one, these would be a microstate. Okay, so this would be like microstate 1, microstate 2, microstate 3. And you can see that they all make the same configuration. The configuration is one molecule has 2, one molecule has 1, and one molecule has 0. If you take a snapshot with your radar detector, you're most likely to see the system in configuration 2. 60% of the time you'll see it in configuration 2. 30% of the time you'd see it in configuration 1, and 10% in configuration 3. In the previous picture, we were only really talking about 3 molecules and 3 quanta energy, which isn't even realistic. Nothing in nature would be that small. Okay, so let's just consider if we had 1,000 molecules, and that's really not very many molecules when you think about it, when moles of molecules are 10 to the 23rd. And we're going to say these 1,000 molecules are sharing 1,000 quanta of energy. The amount of microstates that would be available for these molecules would be 10 to the 600. 10 to the 600. Now think, a mole is 10 to the 23rd. Okay, but this is 10 to the 600. This is more than all the atoms in the entire universe. Okay, so that's just the amount of ways that energy, that 1,000 quanta of energy can be spread out over 1,000 molecules. So if we're talking about using the radar detector again and looking at their velocities and their positions, only the most probable configuration, the one within most number of microstates, would be occupied in reality. The second most probable is so much less likely that we only need to consider the dominant most probable configuration. Whew, okay. Now we have an example of why things happen. All we just had before is just describing it. We just took pictures, we looked at where things were, and we looked at their distribution of basically their speeds or their energies. Now we're going to talk about why something happens. Here we're going to talk about what drives gas expansion. So we all knew, we had that example where we had all the gas molecules in the left, and then we opened the stopcock and half went to the left and half went to the right. Most of you probably could have predicted that would happen on its own. Okay, but why? This diagram here will explain why, and let's just take it picture by picture. In the left picture, we're talking about them being all close together in A, close together, and then in B, they get farther apart when they go into a bigger space. And now let's look in the middle picture about the ladder. Remember we talked about the fan switch, it could only be a 1 or 2 or 3, or like walking up rungs of a ladder. Well, the thing is, the distance between the rungs of the ladder can be different. When the molecules are real close, like in A, the rungs of the ladder are farther apart. And when the molecules are in a larger space, the energy levels are closer together. Why this happens, you are going to have to take physical chemistry for, or quantum physics. There's a mathematical formula for that. But just here, you'll have to take our word for it. When the molecules spread out into a bigger space, there's more energy levels closer together. Okay, but now we're going to say that this pink box here represents the amount of energy that all the molecules have as a whole. The amount of energy that can be spread out between them. This much energy. And if there is more energy levels, more rungs on the ladder that are closer together, there's more possibilities for ways that they can be arranged. Let's go to the final picture. A, where they were far apart, we only had a rung here, a rung here, a rung here. They could only be arranged on different levels. But then once they spread out into a larger space in B, now we have these real close levels. Each molecule, these 5 molecules are in that rung, and these 6 molecules are in this rung. Now, imagine that all of the molecules just decided to move to the left side again. We took a picture and randomly they were all on the left side. Well, what that would mean if they were all on the left side is that they would go back to the bigger ladder again. Okay, so only these rungs would exist now. Okay, so basically this one would be empty, 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 empty. Okay, all of them would have to line up on these levels, and that would never statistically happen. So it's not even that they would all be in the same place that would be statistically unlikely. Also, their distribution of energies would have to go all back to the original ladder, okay? And that would never happen, okay? So we can say statistically, it would be impossible for the location and the energies of the gases to go back into a configuration where they would be all on the left. And this is why gases expand. Okay, this is why if you take the lid off a bottle of soda, the carbon dioxide releases from the bottle and fizzes out all into the atmosphere. So one more time. The number of accessible energy levels increases as they spread out because the level becomes closer together. So more levels become populated at the same temperature. Again, the height of the box was the amount of energy because of one temperature. Okay, the height of the box. Okay, this is the temperature, the amount of energy they have. The energy levels are closer together, but the molecules are in a bigger space. Okay, and that's this ladder. There's more energy levels. Here's something you might have heard before, but maybe you haven't thought about why it happens. Have you heard that heat always flows from hot to cold? Why does this happen? Well, when we look at these energy diagrams, we can actually figure out why. Okay, this ladder. One part of the ladder that's important to realize, it wasn't super obvious on the last picture, is that as temperature increases and increases and increases, okay, so we have higher and higher energy. Okay, we go higher up, the pink box gets higher. The distance between the rungs of the ladder gets bigger. Notice that the levels are closer together down here in the middle. We're looking at the middle picture now, and they're farther up here. Okay, so as you increase energy, the levels or rungs on the ladder are farther apart. In this picture, we're going to start in the middle. Okay, we're going to look at the middle picture. And we're going to say that we have one hot object. Because it's hot, it has more energy than the cold object. We are going to bring them in contact. So maybe you have an ice cube that goes into a hot frying pan. Let's look at the picture on the right. We're going to put the ice cube into the frying pan until it's the ice is melted and the water in the pan is the same temperature as the pan. The pan cools down a little bit and the ice cube becomes water and gets warmer. That's why in the picture on the right, they have the same amount of energy. We've taken this quantity of energy here and moved it over here. If we look at it here, there was 3 levels occupied at the beginning. and there's 5 levels occupied now, and that's because the rungs are closer together when there's a colder temperature. So we went from 3 levels occupied to 5 levels occupied. Or if you look at the bottom total levels, if you counted out the levels that the cold and the hot had, there was 16 levels occupied, and they changed to 18 levels occupied when hot flows to cold. The 3 levels went to the 5 levels. Now, let's say, how can we prove that the ice cube doesn't get colder and the pan gets hotter? This doesn't even really make common sense, but scientifically, why can't the frying pan steal some heat from the ice cube? The ice cube has energy inside of it. How could the pan not get hotter? Well, what would happen there? Imagine we go to the left picture now. Okay, so on the left picture, we have this amount of energy that the cold has. We're going to move it to the hot side. Here in the cold, it had 4 levels occupied. But the same amount of energy as we go higher up in the hot is actually only going to occupy 1 level. And then the cold, of course, we just have a little bit of energy left right there. We had 16 levels occupied in the middle, but if we took some heat from the ice cube and moved it to the frying pan, we would actually only have 14 levels occupied. That is unlikely. The second law of thermodynamics says spontaneous change is driven by the tendency of thermal energy to spread into as many microstates of the system and surroundings as are thermally accessible. Going back to our picture, we started at 16 accessible, we moved some heat from hot to cold, and now there's 18 accessible, 18 occupied. The second law of thermodynamics says that's why that happens. That's why if we put an ice cube in a frying pan, the frying pan doesn't get hotter and the ice cube gets colder. The ice cube melts instead and becomes the same temperature as the frying pan, which also cools down a little bit so they can become in equilibrium. Another way to say the second law of thermodynamics, which might make a little more sense to you, is that nature spontaneously proceeds to the states that have the highest probability of existing. The configurations. Remember we talked about the configuration in the middle, the most probable one is the only one that's ever going to exist. And one other way we can describe the second law of thermodynamics is that energy spontaneously, on its own, tends only to flow from being concentrated in one place to being diffused and spread out. Energy goes from concentrated to spread out. We'll think about that a lot more in this chapter. Whew. I know this is so much. So, Dr. Stephen Lower has a great webpage, and he makes these things called concept maps. And I'm going to steal some of his concept map and go over it with you. It might kind of put things into perspective. At the beginning, we talked about spontaneous processes. That was like the ball rolling down the hill, or the cream diffusing in the coffee, or the ice cube melting, or the tire deflating. Those are processes which, once initiated, proceed to a final state without intervention. The tire is going to go flat. And then they have vanishingly small probabilities of going backwards. Okay, so we proved in this chapter there's not impossible, it's just the probability is super small. Okay, and then because we're talking about moles of things, we're talking about a huge, statistically significant number of particles. And then the final state is when the particles are widely dispersed, like the gas diffusing from the left side to both sides, and or the energy becoming widely dispersed. Okay, that was the bell curves spreading out widely in the frying pan and ice cube becoming the same temperature. Okay, so let's go further down the concept map. Remember, I wanted you to think about the molecules as energy carriers. We say molecules can store and transmit. We'll talk a little bit more about this again. We've already talked about this a lot. Potential energy versus kinetic energy. We have potential energy in intermolecular attractions that are responsible for phases. and in chemical bonds. In kinetic energy, we have rotation, vibration, and translation, which means they're moving, and we'll talk about that again very shortly next lesson. Next, a chemically significant collection of molecules, so a whole bunch of molecules. We're going to talk about its macroscopic state. This is what we can measure. So its pressure, its volume, its temperature, but it's really just a collection of microscopic states, the microstates. And so we can describe a microstate by talking about the position and the momentum. Remember, energy is basically just momentum squared with no sign, no direction. And the microstates are basically infinite. And each individual microstate, like atom number 1 being on the left or being on the right, each one is equally possible, but they make a configuration that's not. The molecules can exchange energy with the surroundings. A spontaneous process is one that occurs when the final macroscopic state, the final pressure or temperature or whatever it is, leads to an irreversible dispersion of energy in the world. The energy has dispersed. The ice cube and the frying pan became the same temperature. And this is because there was an increase in the number of energetically accessible microstates. So remember, we had to talk about the number of microstates in the frying pan and in the ice cube. One way this could happen was the expansion of a gas. We talked about expansion causes the rungs of the ladder to be closer together. An exothermic reaction, we already know when a reaction gives off energy, it's releasing it into the atmosphere, it's dispersing out. Or dissociation reaction, and dissociation reaction was just increase in the number of molecules. And then let's go back over to temperature. Temperature affects spontaneity and direction. Temperature was the amount of energy in that pink box that we had that filled up the rungs. When we make a bigger box, when we have more temperature, it increases the amount of accessible microstates. So more rungs on the ladder can be populated. Final slide, the entropy of the system. It talks about the thermally accessible microstates, the number of microstates. And the entropy increases with number of molecules, the number of energy carriers. They can all go on different rungs of the ladder and be in different places. The temperature, remember we just talked about the height of the pink box. Okay, more microstates can become accessible. More rungs on the ladder can be populated, or you can turn your fan switch up even higher in the car to make that air blast faster. Also increases with volume, because if you're in new locations, you can be in different arrangements. That's when we let the gas molecules go from the left side to both sides. And the molecular complexity, basically this just talks about the ways that the molecule can vibrate or rotate, which when you have bigger molecules, they can go more ways. Don't worry too much about that. We are finally done. This part is why most of the teachers dread teaching about entropy, because students really don't like statistics, and then you're talking about speeds and velocities and whatnot. But if you can kind of wrap your head around this, then it will help you understand the rest of the chapter. We're going to do a lot of in-class exercises to help us practice this, so don't worry if you've watched this and you're not really quite firm with your understanding. We're going to get you through it. Don't worry. All right. Thank you very much. We'll talk to you with the next lecture.